The plane that could save millions, and why nobody dares to build it. Do you know why all commercial airplanes look almost exactly the same? A tube with two wings attached and a tail. Boeing, Airbus, it doesn't matter the brand. They change the colors, they change the paint, but that barrel with wings concept has basically remained unchanged for decades. But here's what's interesting. Inside the computers of aerospace engineers, there has been a design for years that completely breaks this mold. It's called a flying wing, or more precisely, an integrated wing-body aircraft. Imagine an airplane with no clear line separating the fuselage from the wings. The entire aircraft is literally one massive lifting surface. And why does this matter? Because by using almost the entire surface of the aircraft to generate lift, this design reduces aerodynamic drag, improves efficiency, and, in theory, uses much less fuel consumption, more interior space, fewer emissions. It has almost everything commercial aviation dreams of achieving. So the obvious question is, if engineers have been researching it for decades, why hasn't any company built one and put it into large-scale service? The answer is not that the design failed aerodynamically. The problem is that there are three brutally practical barriers holding it back. Let's start with the first one. Barrier 1. Physics does not forgive. When an airplane flies at 10,000 meters, about 33,000 feet, the cabin must maintain pressure that the human body can tolerate. That means the aircraft structure is constantly resisting a massive pressure difference between the inside and the outside. A circular or nearly circular cross-section is one of the most efficient shapes ever created for supporting pressure in a large passenger cabin. When the air pushes outward against the aircraft's skin, the force spreads evenly around the tube as tension. That is why the classic cylindrical fuselage, although it may look boring, can withstand thousands of pressurization cycles while using relatively little material. Now replace that tube with a wide, flat cabin like the one found in a flying wing. That simple engineering advantage disappears. Large, flat surfaces on the top and bottom do not distribute pressure as efficiently. Instead, they create much greater bending forces, and the wider the cabin becomes, the harder it is to control deformation. To prevent the cabin from changing shape during every pressurization cycle, engineers must add more ribs, longerons, support beams, and reinforcements. The result? The fuel saved through better aerodynamics can end up being lost because of the extra structural weight required. And there is an even bigger problem. In a flying wing, the outer skin of the cabin is part of the wing. If that skin deforms due to pressurization, it does not just affect the structure. It can also disrupt airflow and ruin the aerodynamic performance that engineers spent years perfecting. So the aircraft becomes trapped in a cruel contradiction. To save fuel, it needs to be lightweight. To pressurize safely, it needs to be strong. But being strong almost always means becoming heavier. NASA and Boeing have developed advanced composite structures, such as the PRSO's project, attempting to create non-circular cabins that can withstand pressure without carrying excessive additional weight. But even if engineers completely solve the materials problem, that still would not be enough, because waiting right behind it is the second barrier. Barrier 2. 90 seconds to escape alive. Airworthiness regulations for large commercial transport aircraft require something very specific. Under strict test conditions, every passenger must be able to evacuate the aircraft within 90 seconds, using only half of the available exits. If a design cannot meet that requirement, it simply cannot operate as a commercial passenger aircraft. In a traditional airplane, even though the cabin is long and narrow, the layout is organized. The aisle runs from front to back. Doors are distributed along the sides, and evacuation routes are relatively easy to design. But in a flying wing, the interior could be as wide as a theater. Hundreds of passengers spread across a massive fan-shaped space, where people sitting in the center are much farther away from the side exits. And to make matters worse, the same structure requires internal wing beams and reinforcements to handle the bending forces created by the wing. Those structural components cannot simply be cut through like ordinary walls. Every new cross-aisle forces engineers to redesign the entire load distribution system, adding more weight and more complexity. And that creates the scenario no engineer wants to imagine. If a fire breaks out, hundreds of passengers would have to move at the same time toward a limited number of cross-aisles, then squeeze through longitudinal corridors leading to the exits. A design that is physically brilliant, structurally trapped between weight and safety. And there is still a third barrier ahead. The point where engineering collides head-on with certification and real-world acceptance. Closing, the future aircraft that might never take off. And this is where we reach the most interesting part of the entire story. The problem with the flying wing is not that it is a bad idea. In fact, it is the exact opposite. It is one of those concepts that seems too promising to ignore. Engineering studies show that it could offer enormous advantages: lower fuel consumption, greater passenger capacity, more interior space, and a significant reduction in emissions. So why are we still flying aircraft that basically have the same shape they had more than half a century ago? Because in aviation, a revolutionary idea does not only have to be possible, it has to be perfect. A commercial aircraft is not like a laboratory prototype that can fly a few hours just to prove a concept. It is a machine designed to carry hundreds of people every day, for decades, while facing storms, extreme temperature changes, thousands of takeoff and landing cycles, human errors, and emergency situations. The aviation industry is not only looking for the fastest or most efficient aircraft, it is searching for the perfect balance between efficiency, safety, maintenance, cost, and public confidence. And that is where flying wings face their greatest challenge. Because even if engineers solve the structural problems, there is still one massive question remaining. Would the world be ready to accept an aircraft that looks completely different? The history of aviation proves that the most advanced technology does not always win. A clear example was the supersonic passenger aircraft. It was an engineering masterpiece. It could cross oceans in a fraction of the time required by conventional aircraft. It represented the future of air travel, but reality turned out differently. High operating costs, fuel consumption, noise restrictions, and limited demand caused that dream to disappear from the commercial market. The lesson was clear. Engineering alone does not decide the future. Economics, regulations, and public acceptance matter just as much. And the same thing could happen with the flying wing. Imagine stepping inside an aircraft like this for the first time. There would not be a line of windows following the body of the airplane. There would not be that familiar feeling of being inside a long, narrow tube. Instead, you would enter a much wider space, almost like a futuristic room floating in the sky. For some passengers, it would be an incredible experience. For others, it could create a completely different feeling. Because humans have a curious relationship with safety, even when a technology is statistically safer, people often trust what feels familiar. An aircraft with a completely new shape would have to convince millions of passengers that something different does not mean something dangerous, and that may be harder than it sounds. But perhaps the biggest obstacle is not the passengers. It is the airlines.